Okay, so for this question, we have the stable marriage problem, but instead of people always ending up paired, we want some of them to prefer being single to some subset of their mates. And in part one, we're asked to prove that we can get a stable pairing by introducing imaginary mates that people prefer to the ones that they would rather not be paired up with. In other words, these imaginary mates represent being single, or could represent a cat or World of Warcraft or something like that. So if previously you had a particular man and his preferences were, woman 1, woman 2, etc., down to woman K, and those are the people he actually wouldn't mind being paired up with. And then over here there's a break with the people that he actually doesn't want to be paired up with. And basically what you would do is insert an imaginary person. So if we call this man 1, then he has an imaginary person over here after WK. And then the rest of his preference list follows as usual. So then, if you want to think about this imaginary person, what should his preference list look like? Well, presumably this first man can't be rejected from being single. So once he proposes to this imaginary person, he ends up with them forever. So we would expect that man 1 should be the top preference in his imaginary person's list. And similarly for the woman, you could have woman 1 has some list of men, and then eventually her imaginary person, and we'll call the imaginary people for the woman J to avoid getting them confused with I, and so on. So similarly, we'll suppose that J's top preference is the woman that he's matched up to. So in this case, when the algorithm starts running, J will immediately propose to W, and she will remain with him until she gets a proposal from somebody that she prefers to being single. So the question is, does this actually give us a stable matching? So there are a few conditions that we have to check for that. First of all, that there is no rogue couple, and secondly, that nobody who prefers being single to their current partner is within that pairing. So suppose that there's a rogue couple. That's defined so that the man is single and prefers to be with a woman, and that particular woman also prefers him to her current state, or the man is paired and prefers another woman to his current partner. So suppose that this matching gives us a rogue couple. Then we have some man, call it M1, and he's paired up with woman star, but what he really wants is to be with woman plus, and she's paired up with M1 prime. Obviously that would be a rogue couple even without the imaginary people involved. So running the traditional algorithm, that result can't happen. So we don't have to worry about that. So consider the other case, that the man is single and prefers to be with a woman, and in the same way the woman prefers to be with him. So M1 is currently matched up to I1, but he would rather be with woman star, who is above I1 in his preference list, and she's currently paired up with either J star, so she's single, or some man N star, and in either case she prefers M1 to either be in single or be in paired with M star. She prefers M1. Beep. She prefers M1 to either be in single or be in paired with M star. In which case, according to the traditional algorithm, this would still be a rogue pairing using these preference lists. So, by contradiction, that can't occur. So the last case that we need to check is that there's no paired individual who prefers being single over being with his or her pair. So suppose we had a man, again let's call him M1, and he's currently paired to W star, but he would really rather be with his imaginary friend over here. Now the thing is, we know that the imaginary friend will have his particular person as his top preference by default. So obviously if M1 prefers I1, then this would be a rogue couple in the new matchmaking scheme. So in effect, that would also be unstable. And so we have a contradiction that if we run the matching with these augmented preference lists and the extra people, then ultimately we have to have a stable pairing by the new definitions as well. So then the question is, how do we write this out as an actual solution? So we say that given a list of men and women we assume that there are n men and n women, along with their preferences. We add n imaginary men and women, such that the jth imaginary person is inserted into the jth man's preference list above people he doesn't want to be matched with. And similarly for the imaginary men. And the women that they are matched up with. We also assign MJ to the top of IJ's preference list. And similarly for JJ and WJ. for all j's from 1 to n. Then we run the traditional stable marriage algorithm. So, suppose by way of contradiction that we end up with a paired individual who prefers being single over being with his or her pair. So if he prefers being single, then that means that he prefers II to W star. Then this would also be a rogue couple in the augmented matching, because II prefers MI to anybody else. Which gives a contradiction. Similarly, suppose that we end up with a rogue couple where the man is single and prefers to be with a woman who also prefers to be with him. Let's call the woman W star. Then that also forms a rogue couple in the augmented matching. Therefore, the stable marriage algorithm wouldn't have produced it. giving us another contradiction. Similarly, suppose we have a rogue couple where the man prefers being with a particular woman over being with the woman he is currently paired to. And she would also prefer him to her current state. Matched or single. In other words, he is above her single preference J star and also above her current mate, whom we can call M star. Then this would also lead to an unstable pairing. Giving us a contradiction. So by considering all the cases, we have that the algorithm run on the augmented pairing dataset gives a stable pairing according to the new definitions. And we are done. Okay, so for question 2, we want to show that if somebody is single in this new algorithm, then they have to be single in every possible stable pairing. Suppose that we have some stable pairing P1 in which a man is single, so he's matched up to his imaginary person, and some other pairing P2 in which a man is not single. So say he's matched up to W star. Now clearly he prefers W star to being single, otherwise this wouldn't be a stable pairing. In P2 he'd just end up with his imaginary person again because the imaginary person always prefers him. So using Mr. Matchmaker's scheme, we can produce a new pairing P3 where the men have their most preferred partners out of the pairings P1 and P2. So as we said, M1 must prefer W star to being single. So M1 again ends up with W star over here. But every other man also ends up with his preferred partner. And since his preferred partner, if he is not single in either of these, then he must prefer that partner to being single. So the number of men who are have partners has to go up, at least by 1, because M1 ends up paired. and for all the other men, they either stay the same, or if they were single in one of the pairings, they might end up non-single in the new P3. But by contradiction, it's the opposite for women. If a woman is single in one of the pairings, then because Mr. Matchmaker's scheme is pessimal for women, and there's nothing more pessimal than being single, because obviously you can't get worse than being single in this scheme, because the single person will always have you as their top choice, the imaginary person. Obviously the number of single women, has to either stay the same or increase. So the number of single men strictly decreases, the number of single women either stays the same or increases. But since there's an equal number of men and women, that gives a contradiction, because the number of single women has to equal the number of single men. And that's the basic logic here. So to write that all out, we would say that suppose we have two pairings. Since he must prefer his partner in P2 to being single, he will end up with that partner in Mr. Matchmaker's scheme. Which we will call P3. Similarly, any other men who are single in one pairing but paired in the other, will be paired in P3. While if they're single in both, or paired in both, they will obviously be single or paired in P3. So the number of single men must strictly decrease. Compared to P1, which is where we assumed the first man was single. However, for women it's the opposite. Because P3 is pessimal for women, and no one can have a worse result than being single, the number of single women in P3 must be greater than or equal to the number of single women in P1. But that implies that the number of single men strictly decreases between P1 and P3, while the number of single women either stays the same or increases. This is a contradiction because the number of single men and women must be equal. Therefore, our initial hypothesis that we can have one pairing where a man is single and another where he is not single must be false. So we've proven that anybody who is single in one stable pairing must be single in any other stable pairing. The same logic applies to a woman who is single in one stable pairing but not in another pairing, because that would imply that in the pairing where she is not single to P3, the number of single women strictly increases while the number of single men stays the same or decreases, which is, again, a contradiction. Therefore, the hypothesis is true.